We'll now begin section 3 of our Laplace transform. In this section 3, we'll focus on the inverse Laplace transform. We'll talk about the approaches, partial fraction expansion by MATLAB, and we'll go through some examples. The direct way to perform inverse Laplace transform is the equation given to us in the beginning of this course, which is to perform this integration 1 over 2 pi j, the integration from this value to this value, fs e plus st ds. Now it looks very much like the inverse Fourier transform, which is very involved, and typically you will require complex analysis knowledge to perform this inverse Laplace transform using this integration technique. It is beyond the scope of this course, and instead we're going to apply the engineering approach. Let's see now the engineering approach which we'll use. In the engineering approach, we first convert a given fs into known forms, and then use the lookup table. The lookup table that we have examined before have 13 entries, and then we will simply take the lookup table's entry and replace it by the function in time. How do we do that? Is through something called partial fraction expansion. If we have a very complicated fs, we need to break the fs into the simple form that exists in the lookup table. Now, we'll assume that you know how to perform partial fraction expansion. If you do not know, please go through some tutorials on the internet. In this course, at least for the lectures and in the lab, I'm going to use the MATLAB's residual function, which allows me in one command to compute the partial fraction expansion. You should also use this MATLAB residual function to check your answer. Okay, let's try. So what happened? Well, typically we're given fs and we want to find ft. So let's find ft. How do we find ft? Our fs is given in the form that does not exist in the lookup table. What do we do? Well, we want to convert this form into much simpler form. Well, that looks like this. So on the left is we have the polynomial numerator as a polynomial, and the denominator as another polynomial of n degree. On the top is m degree. However, there is no lookup table that have this form. Instead, the lookup table would often have this form. We want to convert from the left to the right. If you have MATLAB, which is a one statement affair, you enter the coefficients of the numerator as a vector b, the denominator as another vector a. You send b and a into this function called residual, and out comes rpk, which is 3 vectors telling you the coefficients of r, which is the numerator on top, and k below. That's all. Okay, so what we are trying to tell you is that there are functions in MATLAB that can help you solve this kind of problems. However, of course, in the exams, you're expected to do partial fractions by hand. But what you need to do is to use the residual in the lab as well as your tutorial to verify your answers. Let's proceed to have some concrete examples. Okay, let's proceed to the next page, which is page 27 of the slide. In this page, we're given this function equals to xs. And we're going to break these functions into this form, where this form would have entries in the lookup table. Here, the answer is something called two real poles, where we have two real poles here. S is at pole at -2 and S is at pole at +3. Right, how do we go from the left hand side to the right hand side? This is called partial fraction expansion. And then how do you go from the right hand side to the left hand side? All you need to do, if you have K1 and K2, is to collapse the two equations together by multiplication. Now, let's see. Please go through how to find K1 and K2 by hand. This is the method. And what we show you is that the answer is in this form. Let's just have a very quick calculation to check that the right hand side is equals to the left hand side. What should we do? Well, we'll go from 4 multiplied by S minus 3 plus 3 multiplied by S plus 2 divided by S plus 2 S minus 3. Let's further work out. 4S minus 12 plus 3S plus 6 divided by S squared plus 2S minus 3S minus 6. And the answer is 7S minus 6 divided by S squared plus S minus 6. Is that right? S squared minus S squared. Oh, did I make a mistake? Oh yes, here is the mistake. It should be minus S minus 6. So what you do is that if you find the coefficients by hand, which is quite difficult, well, mechanical but difficult, error prone, you can then use this operation to then check whether your partial fraction expansion is correct or not. Now, once you have the XS in this form, then it is trivial. Why do I say that? Look at this. This entry have a lookup table. This entry has a lookup table. What is the inverse Laplace transform? Is simply the inverse Laplace transform of 4 over S plus A is equals to 4 inverse Laplace transform of 1 over S plus A, which is equals to 4 E minus AT. And what is A? A is, in this case, plus 2 will become minus 2t here. Alright? So you can do the rest. The second term will become 3e plus 3t, and then we have the Heaviside function. Now, look at this very carefully. As time goes to infinity, this guy goes to 0. But when time goes to infinity, this expression will blow up. Okay, and we don't like that. So later on, we'll show you how to study stability of systems. Now, how to do partial fractions using what do you call that? MATLAB. This is trivial. What you do is this. Get this numerator and just put the coefficients down. 6, minus 6, sorry, and 7. And the other guy is 1, minus 1, minus 6. So we call this typically the B, and this is the A. So B is 7 and minus 6, and A is 1, minus 1 and minus 6. Right, we then use this equation, or we call this function with B and A. It's called residual, and we get 3 parameters out. or 3 variables out. That's the solution. R, P, and K. R is a vector with 2 elements. So this is called R1 because MATLAB uses index starting from 1. This is P. So this guy is P1 and this guy is P2. And K is nothing. So the answer is in this form. R1 divided by S minus P1 plus R2 S minus P2. Remember, this is minus here, so when the entry of the pole is minus, it will become plus. Alright, so just go through this and you'll see the inverse Laplace transform for the first example. I'll now quickly do the inverse Laplace transform, second example. Again, you have to do it by hand, but I'm going to do it with MATLAB. We are given Fs is equals to this expression here. We set B is equals to minus 4 and 8. And we set A is equals to 1, 6, and 8. We use residual to find the RPK. The R is here. This is R1 again. This is R2. This is P1. And this is P2. And K is nothing again. And therefore the answer is R1 over S minus P1 plus R2 S minus P2. You plug this in, you can see that P1 is minus 4. So minus minus 4 become S plus 4. P2 is minus 2. S minus P2 becomes S plus 2. R1 is minus 12. That's correct. And R2 is 8. That's correct. So once we have this, of course, the next step is simple. F of t, and we use the lookup table, which is minus 12, e minus 4t plus 8, e minus 2t. And if you really want to be pedantic, it's ut here, causal signal. Well, that's it for this example 2.